Welcome to episode 122 of George's Random Astronomical Object. Every episode, I run a random number generator to select random astronomical coordinates in the sky, and I then search for an astronomical object near those coordinates and talk about what makes that object so interesting to astronomers. So I will now run the random number generator.
Yep. Yep. Yep.
The coordinates from the generator for this episode are 11 hours, 49 minutes, 38.5 seconds right ascension, and plus 22 degrees, 23 minutes, 55 seconds declination. These coordinates point to an object named MAX J1149.5 plus 2223. This is a cluster of galaxies in the constellation Leo. The acronym MACS, MACS, stands for the Massive Cluster Survey, which was one of the surveys that discovered the cluster. The letter J and the digits indicate the coordinates of this object. I could not find a good estimate for the total number of galaxies within this cluster, but it's probably in the thousands. The total mass of the cluster is somewhere around 2 or 3 quadrillion times the mass of the Sun, or somewhere around 1,000 times the mass of the Milky Way, and the cluster has a diameter of about a few million light years, although it's a bit difficult to actually state where the edge of a cluster of galaxies is. The light from the cluster MAX J1149.5 plus 2223 has taken 5.4 billion years to reach us, but the distance in light years is not exactly equivalent to the light travel time for complex reasons that I'm not going to get into. A few different techniques can be used to find clusters of galaxies. The classical technique is to stare at images of the night sky and look for locations with lots of galaxies. This is the technique that George Abell used in the mid-20th century. However, in spite of the fact that George Abell was an expert at staring at things, he could only find a limited number of clusters this way. Another technique is to look for the X-ray emission associated with a very hot gas in between the galaxies within these clusters. In the 1990s, an X-ray telescope named ROSAT made maps of the X-ray emission from the entire sky, and a couple of surveys working with the X-ray data from that telescope, including the Massive Cluster Survey, or MACS, MACS, published results at about the same time, identifying the object now known as MAX J1149.5 plus 2223. As a side note, I was a student at the University of Hawaii at the same time that Harold Ebeling and Pat Henry at the University of Hawaii were working on the MACS survey. Anyway, MAX J1149.5 plus 2223 is not just a nice spherical cloud of galaxies orbiting within the nice spherical blob of X-ray gas. The cluster is actually a little elongated and lopsided, and the gas appears to be moving around somewhat chaotically, with at least one giant shock wave passing through the gas within the cluster. This, along with the motions of the galaxies within the cluster, indicate that MAX J1149.5 plus 2223 was made through the collision of 3 smaller clusters around 1 billion years before the point in time that we are seeing the cluster. As a reminder, the light from this cluster has taken about 5.4 billion years to reach us. Give it a couple more billion years, and if no other collisions take place, maybe everything will calm down within the cluster. One of the really cool things about MAX J1149.5 plus 2223 is that it is so massive that the gravitational forces from the cluster can bend the light from more distant galaxies behind the cluster. This phenomenon is called gravitational lensing. In MAX J1149.5 plus 2223, the gravitational lensing has caused some of the background galaxies to appear in multiple places in the sky as seen from Earth. The light from these background galaxies may also appear brighter than they would without the lensing. This phenomenon can be used to measure the mass of the cluster, which is very useful given that the chaotic nature of the cluster makes it difficult to try to use the orbits of the galaxies within the cluster to determine its mass. However, MACS J1149.5 plus 2223 has not just gravitationally lensed light from a bunch of boring background galaxies. Some of those galaxies are actually really, really far away. One galaxy, which was named MACS 1149-JD, is so far away that we are seeing the galaxy about 500 million years after the Big Bang, and the light has taken about 13.2 billion years, or most of the lifetime of the universe, to reach the Earth. MACS 1149-JD was either the most distant galaxy known or close to being the most distant galaxy known in the universe when it was discovered in 2012, and as of this time, it is still among the most distant known galaxies in the universe. And it is only visible because the gravitational lensing effects and the cluster MACS J1149.5 plus 2223 have boosted the brightness of the galaxy. Astronomers have been looking at the galaxy MACS 1149-JD in detail to understand how galaxies are forming in the early universe. However, this really distant galaxy, as impressive as it is, only wins the runner-up reward in terms of the most interesting things that were gravitationally lensed by the cluster of galaxies MACS J1149.5 plus 2223. The first place award goes to the gravitationally lensed supernova behind the cluster. Discovered by a group led by Patrick Kelly, the supernova first appeared in November 2014 in 4 locations that formed a cross-shaped pattern in one location within the cluster. After a little over a year, the supernova appeared in a 5th location outside the cross pattern, but sort of nearby. This is not only because the gravitational lensing bent the light from the supernova in multiple different ways, but also because the time it took the light to travel these different paths was different, with the light taking less time to travel down the 4 paths that made the cross shape and more time to travel down the path to the 5th location. This object was named Supernova Refstal after the Swedish astronomer Sir Refstal, who'd written a paper in 1964 stating that if anyone is ever lucky enough to find a supernova affected by gravitational lensing, it can be used to measure the Hubble constant. Because of the expansion of the universe, most galaxies appear to be moving away from our own, and galaxies that are farther away appear to be moving faster than galaxies that are nearby. The Hubble constant relates the speed at which galaxies are moving away from the Milky Way to their distance. Sir Refstal's idea was that a supernova produces a lot of light for a very brief period of time, but when that light is gravitationally lensed and appears in multiple locations, as seen from Earth, the light from the different locations on the sky will take different amounts of time to reach the Earth, and the difference in time between when the supernova appears in each different location is directly related to the Hubble constant. It literally took 50 years after Sir Refstal's paper before anyone found a supernova, more specifically supernova Refstal, in MACS J1149.5 plus 2223, where they could apply his theory to actually measure the Hubble constant. Patrick Kelly's group published 2 different estimates of the Hubble constant based on different sets of models describing the gravitational lensing. One set of models gave a Hubble constant of 64.8 km per second per megaparsec, while the other set gave 66.6 km per second per megaparsec. For comparison, the Hubble constant has also been measured using 2 other techniques. Using the brightnesses of, quote, ordinary, unquote, unlensed nearby Type 1a supernovae, astronomers have calculated the Hubble constant to be 73.0 km per second per megaparsec. I talked about one of these Type 1a supernovae very recently in episode 118. Go listen to that episode if you want more information on how the brightnesses of unlensed supernovae are used to measure distances. The other technique for calculating the Hubble constant has involved modeling the cosmic microwave background radiation, which is the afterglow left over from the Big Bang. That has given the Hubble constant of 67.4 kilometers per second per megaparsec. The people who work on the brightnesses of Type 1a supernovae and the people who work on the cosmic microwave background radiation have spent quite a bit of time trying to figure out whose results are correct. The Hubble constant from supernova Refstal is more consistent with the Hubble constant from the cosmic microwave background. This would be rather interesting, as it would indicate that people are modeling the cosmic microwave background radiation well, but that people's models of Type 1a supernovae might be a little off. Quite honestly, I've always been a little worried about the supernovae results regarding the expansion of the universe, and these results from supernova Refstal just make me feel a little bit more worried. In any case, I think that these results are quite revolutionary and could potentially lead to scientific consensus on the exact value of the Hubble constant. So that's my summary of the cluster of galaxies MACS J1149.5 plus 2223, and the location on the Earth's surface corresponding to the position of this cluster in the sky is a location in the Pacific Ocean in the triangular region made by Midway Atoll, Wake Island, and Johnston Atoll. As best as I can tell, a lot of random ships pass through this area traveling between East Asia and the west coast of North America. But, very interestingly, few aircraft seem to fly through the area. Go figure! The website for this podcast is www.randomastronomicalobject.com. You can visit the website to read information about the astronomical objects, view images of those astronomical objects, look up additional reference information, and send me random feedback. The audio was recorded and edited by George Bendo. The music is Immersion by Sasha Endy at www.sasha-endy.de, and the sound effects are from the Freesounds Project at www.freesounds.org. Thanks for listening.